So this section 1.2, is about classifying real numbers, some of their properties that make it so that we have a little more flexibility on how we can maneuver an equation, an expression. Yeah, we have to stick by the rules of order of operations, but we got a little bit of wiggle room, okay? Now, as far as the types of real numbers go, this little graphic, I think, is really helpful, okay? The R stands for the real numbers. Now, if you are to type it, just put a capital bold R. If you're to write it, the way that my math instructors taught me in college, you just make an R with a double back to it. Capital R, double back to it. If you're typing it, just make a capital R and make it bold, okay? So those are the real numbers. It's any number on the number line. So any number that can be represented on a number line would be considered a real number. So fractions, decimals, percents as a decimal. Irrational numbers, weird numbers like pi, all those numbers would be considered real numbers. And that's why if you look in the graphic, the R is around the entire set, okay? And that's on purpose. Now, once we have decided, hey, it's a real number on the number line, the next two ways we think about it are irrational and rational. The irrational is represented by a capital Q. No, it isn't. It's an I. I'm jumping ahead of here. Rational is a capital Q. Irrational is an I. Okay? Rational is a Q. So you can think about our real numbers. If we look at this graphic, we've kind of broken it down into two halves. The Q is our rational. The I is our irrational. I and Q. Now, let's talk about irrational first, because it's the easiest one in a way. That's numbers like pi, that 3.1415926 that keeps on and going. If anyone that's typing, if you do that symbol, insert an equation, there's a pi symbol there you can type. And E. So if you did exponential functions at all in Algebra 1, I don't know if you would have gotten to them. E is a number that actually shows up in nature a lot. It's about 2.71828, I think it is, approximately 2.7. There is a button on most calculators, even those red ones, that has an E. It comes up in nature a lot. Those are those decimals, never stop or repeat. Okay, so repeating decimals do not count in this category, but things like pi and E, those are decimals that never stop or repeat. Square root of 2, that's another one. Square root of 7, those square roots that don't come out great. Okay, so once they're irrational, we're kind of done describing that set. There is a type of irrational numbers, if you were in upper level math, called transcendental ones. Those ones you wouldn't explore in a high school class, but if you ever take math in college, you might. Now, what's Q? Q is a rational number. It is any number that can be represented as a fraction. Now, if you're writing a number as a fraction, usually they're going to represent it as A over B. So if we actually focus on the decimal stops or repeats. So it's the opposite of irrational. Decimal stops or repeats. Mathematically, you say that the decimal terminates, it stops. Or repeats itself, like 0.27, or 0.272727. .333333.888. I will show you some different methods to find out, if you know that decimal, how to jump to the fraction if we get to it, okay? Now, once we're in the rational world, these three are types of rationals, so they're even more specific for those sets. Integers, I'm just going to write it in set notation, so I can't make brackets real great, but you'll see. Bracket, put the 3 dots, meaning it goes to the left. You want 3 dots, it is a mathematical thing, actually. And then, like, let's go -3, -2, -1, 0, 1, 2, 3. And then 3 dots on the other side. Mathematically, in set notation, that just means that pattern repeats indefinitely to the left, this one to the right. So it actually is, it does mean an indefinite pattern. The abbreviation for an integer, I think I was already used, it's actually Z. And so if we look back over in this set, that is the largest specific set that's in blue there, that's Z. Whole numbers. Now, there is some books that do not separate these two. They just kind of, they're lumped together. But whole numbers, that's going to be abbreviated a W. And that's just from 0 and in the positive direction. So it is an integer, but specifically, you throw out all the negatives. So it's a type of integer. That's why its circle is inside the integer spot, that W right here. Because they are integers, they're rational, because you can just put them over 1 and you can see what their fraction is. And then lastly, natural numbers. Sometimes they are called counting numbers. Depends on the textbook. Like I said, some counting numbers include 0. Most do not. I am not. I think of as counting numbers or natural numbers. Think about when you are teaching a little one how to count. You don't tell them 0, right? You count 1, 2, 3. If you look at math history, humans did not add a symbol for 0 until very late in the game. They had lots of symbols for 1, 2, 3, 4, and so on. Not many cultures had a symbol for 0. I think it was in the Arabic culture that they added 0 as one of the first ones, and it maybe in the Chinese symbols they did. But it wasn't. We don't count that way. We don't teach ourselves to count that way. 0 is just I have nothing, and so in many cultures they didn't have a symbol. They just said, well, I don't have anything, and so. When you think of natural numbers, think naturally, how do you count? 1, 2, 3, 4. And whole numbers throws in the 0, integers throws in the negatives. Okay? But know the symbols. It'll be helpful as we learn some notation that you might use in a pre-calc class. Okay? Any questions about the stuff you see there? Okay. Now let's classify the numbers that we see here. Now the first thing you always ask yourself, is it a real number on the number line? All of these numbers are real. I can never make this very good. There we go, that's a little better. All of those numbers are real. The numbers that will not be real will include that I. Do you remember in Algebra 1, did you guys do anything with that imaginary number I? If it has an I in it, it's not on that list. None of those have that I in there. They're not on that list. The next thing we ask ourselves, are they rational or are they irrational? Can they be rewritten as a fraction? Can they be rewritten as a fraction? -23 can be written as -23/1. So it's rational. It's a Q. Square root of 50. If you threw that into a calculator, you get decimal 7.07106, blah, and it never repeats and it never stops. That's irrational. That's an I. So we're done with B. As soon as it's irrational, we don't have to go further. Okay? We can clearly see that -4/9 is written as a fraction. It's a Q. 100, we could write 100 over 1. It's a Q. So again, I look on the list. If they don't have an I in it, you know it's real. Next question you ask yourself, is it a Q or an I? Is it rational or irrational? Rational, rational, rational. Only one that's funky is square root of 50. It's irrational. Okay? So we're done with B. It can't be anything else. Now we have to look at A, C, and D. Can we go further with those? The next more specific group are the integers. Remember that was that list, -3, -2, -1, 0, 1, 2, 3. Okay? This is an integer. That's Z. C is not an integer. We're done. D is an integer. Yep, it's on that list if I were to keep that going to the right. Okay, so that's an integer. Let's talk about whole numbers. The next list is our whole numbers. Is -23 on the whole number list? No, it's negative. Remember, whole numbers are 0 and the positives. So cross that. We're done with that one. So now the only one we're left with is the number 100. Is it a whole number? Yeah, it's on that list, of course. That's a W. If a little kid was learning to count and they kept going and counting, would they count to 100? Yeah, that's a natural number. Okay? So I kind of do that same thing anytime I'm classifying numbers. Is it a real number? Check. Okay, if it's a real number, is it rational or irrational? If it's irrational, you're done. If it's rational, is it anything specific? Next thing is integer, then whole number, then counting number, natural number. Okay? Makes sense how you classify them? Kind of, maybe a little bit? Okay. Let's talk about some properties. Now, I'm not going to completely think about the properties you did in geometry and how you had to name them and had to show them and stuff. We are probably not going to be that specific in here. I need you to know how to use the property more than I need you to know how to just say, that's the property I used. Okay, but let's talk about them. Commutative property. That is A plus B equals B plus A. There's an additive commutative property. There's a multiplicative commutative property. 2 times 3 is the same as 3 times 2. 2 times 3 is the same as 3 times 2. We instinctually know the commutative property. The way to remember it, I am commuting to work. I am going back and forth to work. So the order of multiplication doesn't matter. The order of addition doesn't matter. Division matters. Subtraction. There's no property for those, okay? Associative property. I'm writing it without the parentheses for a moment to show you how you can identify associative. Associative property for addition, at first, B wants to talk to his friend A. On the other side, B decides to first talk to his friend C. Okay? So you notice the order of my ABC didn't matter. The order was the same. ABC, ABC. What matters is the association. A wants to associate with B first. Here, B wants to associate with C first. So it's the association. Okay? You can take out the plus symbols for associative and you can make it multiplication. Multiplication is associative. So you can do a multiplication in order from left to right. You know, we could do A times B, then times C. But if the numbers work nicer for us to associate the back ones first, then the second one, it's okay too. So it's just a matter of the rules that you learn from back in your multiplication tables and stuff. Sometimes you can manipulate the order a little bit so that it works a little nicer for you, okay? Identity. The multiplicative identity, well, let's do additive first because I've been doing additive first. For the additive identity, it's just the number 0. A plus 0 is still A. It doesn't change its identity when I add 0. So for addition, A plus 0 equals A. This is your identity. For multiplication, what do you multiply by a number so that you don't change the number? 1. So that is the multiplicative identity. So that just means if I want to not affect the number, but I need to add something, add 0. If I want to not affect the number, but I need to multiply by something, put on a 1. So those are things you know. But if you ever see anything mentioned about identity, that's what that means. There is an additive inverse. Additive inverse is something you can add on so that you get 0. And so that would be the opposite. Multiplicative, what can we add on to get, or I'm sorry, multiply by to get 1? And so that's the reciprocal. Actually, let's go A over B times B over A, because then that'll even more specifically show reciprocal. One type of our rules, of our properties that you may not have focused on too much in an Algebra 1 class is this next one, this closure. All that means is a set is closed under an operation if, when you do that operation, you still get a number in the set. I could right here. A set is closed under an operation if when you do that operation, you get a number in the set. Okay, let me give you some examples. The integers are closed under addition and subtraction and multiplication. If I add 2 integers, still getting an integer. Subtract 2 integers, still getting an integer. Multiply 2 integers, still getting an integer. What about if we divide 2 integers? Are we going to get an integer every time? No. So it would not be closed under division. And that's kind of the way it works. I mean, if I do the operation, am I still going to get numbers in the set? That's what that means. We're not going to use it too much, but it is a word that might come up, and so I just wanted to make sure you knew that vocabulary. And then lastly is our distributive property. So if we have A times the quantity of B plus C, we actually, I think, did one in our review. This A can break the barrier of the parenthesis. It's going to multiply in, so A will multiply by the first term plus the addition of A multiplying by the second term. If there's 3 terms, you multiply by each one. If there's 4 terms, you multiply by each term. It doesn't matter how many there are. The distributive property allows us to open up a parenthesis if there's no other way for us to do it. So it is a helpful tool in the whole, world of mathematics, especially equations. Okay. So those are our properties. Hopefully you have those written down. Do we have any questions about the properties? You probably did them back in the day. And probably even a little bit in geometry, you would have come up with those properties. Okay, so example 2 here says what properties are used. Now, when I see a list of things, I check, do I see the same operation? Yeah, it's multiplication. And then the next thing I check for is, did the order change at all? Because if the order changes, it's probably commutative. If the order didn't change, it's probably associative. So it goes 5, 4, 13 on both sides. So the order didn't change, it's not commutative. There's not an addition and a multiplication, so it's not distributive. But you see how the parentheses have changed location. And that tells me that it is the associative property. Now, if you specifically say the associative property of multiplication, that is the most formal way. But I'm never going to be like, oh my gosh, please say the associative property of, you know what I mean? But it's technically, there's an associative property of both multiplication and addition, but as long as you tell me that. Okay. So that's the associative property for A. What property do we clearly see is happening in B? Yeah, that's that distributive property, isn't it? So that 2 has multiplied in. So when you see multiplication and addition within the same problem, that's going to be your distributive property. Everybody see how those properties work for those two? Okay, so now let's talk about finding the additive and multiplicative inverses. Remember, the additive inverse, we want to get 0. So this is going to be the opposite. The multiplicative inverse, we need to multiply and get 1. So this is going to be the reciprocal. So when you read additive inverse, think opposite. Multiplicative inverse, think reciprocal. If you jump to that in your head, you're going to get it right every time. So first, let's do the additive. Okay. The additive inverse is nice. To get 0, all we need is the opposite. So you don't have to do much of anything. They're wonderful to find. So that's positive 5/8, negative 1.25, and negative 2.5. So we don't really have to do much. It's just the opposite. So if it's positive, make it negative. If it's negative, make it positive. Additive inverses are wonderful. The one that's going to cause us to have to do a little bit more work is the multiplicative inverse. We have to find the reciprocal. Now, the way I see A, the reciprocal is pretty darn nice. We just get to take that fraction and flip it over. And so it's negative 8/5. You can check that it's right, because if we multiply negative 5/8 and negative 8/5, we should get a positive 1, which we do. We would get negative 40 over negative 40, which is positive 1. So think about how nice that was to do that. And then let's think what we have to do to fix B and C so that we can make it work. Okay? Now, 1.25, to find its reciprocal, I want it in fraction form. So that's 25ths. 25 is in the hundredth spot is what I meant, I'm sorry. So that's 125 over 100. So if we use the place value of the decimal, we can make it a fraction, okay? Please reduce it as much as possible. Both top and bottom are divisible by 25. If you see 5 and then go 5 again, that works. You don't have to jump to 25. But if you divide the top by 25, you get 5. You divide the bottom by 25, you get 4. You can check in a calculator, 5 divided by 4 is 1.25. So however you get to the fact that 1.25 is equivalent to 5/4, go for it. You can think of how many quarters would it be to make $1.25. There's 5. You need 5 quarters. However you want to do it. Once you have that fractional equivalent, then its multiplicative inverse, you just turn it upside down. And so its inverse is 4/5. Now, you can check on a calculator, and I'm going to show you 2 different ways to use one of those red calculators. But if you do 1.25 times 4/5 on a calculator, you're going to get 1 if you did it right, okay? Another thing you can do, I don't know if you knew what this button was. See this button right here? X to the negative 1 power? That is the reciprocal button. You might not have known that on those red calculators. So if at this time, if you put in 1.25, hit that button, I don't think you have to press equal. Tell me, does it switch it immediately? Or do you have to hit equals? Huh? Okay, so if you hit equals, does it say 0.8? Yeah, 4/5 is 0.8. Okay, so that's another way if you want to use a calculator, but I need you to, again, kind of move away from the calculator, but you can check your work on a calculator very easily. 2.5. Do you remember back in somewhere in maybe 3rd or 4th grade, you started practicing making that into an improper fraction? You know the rule where you do 2 times 2 is 4, 4 plus 1 is 5. Remember that? That's 5/2. So if you switch that to its improper form, all you got to do then is flip it over. And so that's really nice. So 2/5 is the multiplicative inverse. Again, your calculator can guide you if you're correct or not. 2.5 times 2/5 better be 1, or it's not the multiplicative inverse. Okay? Everybody good with finding additive and multiplicative inverses? So it's just associate additive inverse as the opposite, multiplicative inverse as the reciprocal, and you'll be good to go. 2 more examples, and then you'll have some time in class to work on the homework. Both homeworks are due tomorrow. You'll have time in class tomorrow, and that's all we're doing tomorrow. I give you time to work on that assignment so you can ask me questions and do all that. Okay, last 2 examples. Here it says that Kayla makes $8 per hour working at a grocery store. The number of hours Kayla worked each day in 1 week are given there. How much money did Kayla earn this week? Now, mathematically speaking, see how they mention it's the distributive property. Technically, you can do 8 times the sum of those things. Okay? So one way to calculate this, if we follow order of operations, is to sum up the total hours, and then we're going to multiply by 8. So that's one way to do it. Or we can calculate the money she makes every day and then add them up. So let's do it both ways to show that the distributive property does indeed work. Now, if we were to actually distribute, we would do 8 times 3. 8 times 2.5 is 20. 8 times 2, 8 times 1, and 8 times 4. Okay, so that's one way to do it. So if we distribute, that does work. So we're calculating really the wages we earn every day. Another way is to add up the hours first and then multiply by 8. And you get $100. Now let's make sure I did the other ones right, that I actually get $100. Because I did do it in my head. Yeah, so it's just illustrating that we can distribute. We could have added first and then multiply by 8. Both methods work, and this distributive property works. Okay. So the last one I want to do is to simplify an expression with the distributive property embedded into it, just to make sure we remember that rule. Okay. So if we see anything sitting next to a parenthesis, that is implying the thing that's sitting and touching the parenthesis is going to multiply. So all you're going to do is you're going to take the 3 and you're going to multiply it first by both things. So 3 times 4x is 12x. 3 times negative 2y is negative 6y. Okay? Because we have jumped into the parenthesis, we have used it, the parenthesis is no longer necessary, drop it away. Okay? Now we're going to take, and here's the part that some of my students in the past have made mistakes on. It's the negative 2 that we are distributing. So make sure that you think of this as not a 2 distributed and you just bring down the negative. You are distributing a negative 2 to each of those. Otherwise, your signs will get all wonky. So please make sure to distribute the negative with it. Negative 2 times 3x is negative 6x. Negative 2 times positive y is negative 2y. Now, once you have that listing, then it's just a matter of, because they want you to simplify, just check for like terms. I tend to kind of stick alphabetically, If it's powers, I kind of go from high to low. Try to get an organizational system so you don't mess something up. Can anybody tell me two terms that you notice are like terms there? Can anybody share with me what like terms? What do you see? Yes, this 12x and this negative 6x are like terms. So that means you can add the coefficients and you keep that variable. So 12x minus 6x is positive 6x. Are there any other like terms we see? Ian, what you got?
Negative 6y and negative 2y.
You got it. Those are like terms. They're the same sign, so we're going to add them up and keep the sign. So that's negative 8y. Now, there are times, let's say eventually, if we might need to graph something, if we might need to find more information, we might do something further, but don't overthink it. You guys are smart. You're going to want to overthink it. That is your answer. Stop there. Okay? Any questions about the notes? Yes?
Can you go back to the one?
Which one?
Natural numbers.
Yes, I can. I just got to find it. There we go. Okay. So the homework is just below it. Most of the time your homework is going to be digital, just like you saw in 1-1. So now if you could, let's all take a look at the homework that's underneath, okay? We have some people writing something down, but in a second we're going to jump to the homework, okay? So if you jump to the homework, most of the time I am going to either highlight what's there. If there's any circles that are written in pencil on the paper, ignore them because they might not be right. Just read what we got here, okay? We're going to do the odds, but also if you can add in 36. So I'm just going to highlight those on mine so that if we have questions, we can kind of focus on there. And I don't know why I said 1 to 63 because it really starts at 19, but 19 to 63 odds. And add in 36. And 36, yeah, okay. Now, we don't have a ton of time today. And that's okay. So again, it's always written at the top. We don't have a ton of time today. And that's okay. You're going to have all tomorrow's class period to get your 1-1 and 1-2 homeworks turned in. It is not a bad idea to start it tonight. I had some really good questions last night that people were asking. Or when you walk into the room, then you have questions I can answer while we have class time. But tomorrow, you'll be able to work on your homework, ask me questions, and again, everything, I try to post everything on Google Classroom. That's where you'll find your homework most of the time. Okay, any questions? Okay, work on your homework. We're going to have time tomorrow. Tomorrow we'll finish it up. And next week we will have our first quiz. Once we get a little closer, I always do a little quiz review. I'll give you that information next week. Okay, so there you go.